Well, welcome back. This is part 2 of electrostatics. We're going to do one last problem in part 2, and this is involving calculus. Alright, so in this problem we're given a semicircular rod with a uniform charge density of lambda, and we're asked to find what the electric field is at this point. So from what we know that we can superposition the contribution of electric fields, so it would be the sum of all of these contributions from small sections dq. So we can write this as the electric field is equal to the integral of dE, and let's choose a theta. So let's say theta is the angle from the vertical line. So it would be equal to dE cosine theta. And we also know that dE is equal to k dq over r squared. Now we don't know what dq is, but from our uniform charge density we can figure out what dq is. So we know that it's also equal to q over L, which is the total length of this rod, and it's we can also write it as dq over ds, and ds would just be a small portion of that rod. So then we can write dq, and we'll switch to lowercase q. dq is equal to lambda ds, but ds is also equal to r d theta. So that's what our dq is. So now we can write this integral as the integral from negative pi over 2 to pi over 2 of k lambda r d theta all over I squared times cosine theta. And we're integrating by theta, so our antiderivative should have sine theta. So in the end we will have something that looks like, and we can rewrite k as 1 over 4 pi epsilon naught, and then it would be lambda over, you see that these two r's leave only one r in the denominator, lambda over r sine theta, evaluated from negative pi over 2 and pi over 2. So just evaluate it, and your final electric field will be equal to 1 over 2 pi epsilon naught times q pi over L squared. And the reason why there's no lambda in the final answer is we've replaced lambda with q over L. And if you want to simplify this further, L is just 2 pi r over 2, which is just half the circumference of this circle with radius r. So whenever you're given a problem where you need to find the total electric field's contributions, just keep in mind you can sum up all the individual contributions, but you do need to take into account of the direction. So this is why we have cosine theta. And to make it a little more clear, I didn't mix up, but I could make it a little more apparent. So theta is actually this theta. So it's taking the cosine of that theta, but it's also this theta. So you're integrating from pi over 2 to negative pi over 2. Lastly, let's talk about Gauss's law and electric field lines. So first we'll go with electric field lines. This should be really simple. When we're given a point charge, the electric field lines will go out like this. It will go out radially in all directions. You get the point, and all of them should be the same length. And if we're given 2 point charges, they will sort of bend away from each other in the middle. So something like that, and you will just have all your arrows out like that. And it's quite easy to imagine what it looks like for other setups. And now let's move on to the last topic, Gauss's law. We also know that integral of e dA is also equal to q enclosed all over q enclosed over epsilon naught, and epsilon naught is the vacuum permittivity number, and that is about equal to 8.85 times 10 to the negative 12th farads per meter. Don't confuse this with force. This is farads. So if we have like a cylindrical conductor, which with a charge of plus q, we can figure out what the electric field is at a point away. Let's say over here. We simply use a Gaussian surface, so we know that, and let's say that point was distance r away. Then we can write this as E times 4 pi r squared equals q over epsilon naught. And we can find what E is. E is 1 over 4 pi epsilon naught, and this is really just k. So it's basically kq over r squared. And if we were to also put another shell on the outside. So here, let's redraw this diagram. So if it was something like this, if you imagine it like that, and both of them were conductors, then it would, the plus q would make the outside shell polarized to a negative q, and if the outside shell had a total charge of 0, then it would be minus q on the outside, minus q on the inside, and plus q on the outside. And if we were to find like the electric field at a point over here, we would realize that q enclosed, right, this negative q and this positive q, it would cancel out. So in the end, right, E would just be equal to 0. So this pretty much wraps up electrostatics. If you need any extra practice, I've posted some problems in the description below.